Okay, hello, welcome back. Now we are equipped with enough tools to study the rotational kinetics of rigid bodies. But for now, let's stay on planar motion. Rotation in 3D is complicated. We don't go there. We don't like that. Only Euler liked it. Okay, so quick recap. In the translational domain, we had sum of all these external forces equals mass times acceleration of center of gravity. This was the translational equation of motion. Now, I'm not going to provide the proof. Proof is in the textbook. What you can do, calculate for the rotation. Let's do this translational. I think I'm gonna need more space. Okay, it's fine. And for rotational, you can calculate moment of all external forces about center of gravity or center of mass equals moment of inertia about center of mass times angular acceleration. So this body is turning with some angular acceleration. And note how beautiful it is. The parallel between the translational and rotational. Everything works out the same, except you're calculating essentially everything in rotational domain. So these external moments are the moments of all external forces about the center of gravity. So for instance, if you want to calculate moment of this force, you find the perpendicular distance, let's call it d3, and calculate the moment. Note that this is in general, this is a vector equation, but because we are in 2D space, and looking at planar motion, we can assume some directions of positive rotation, and as long as we stick with that positive, calculate all moments if they are in the same direction, calculate those as positive. If it's opposite, calculate as negative. We will be fine with just the scalar equation. Let's call this vector equation just because they're easy to calculate either way, either scalar or vector form. Yeah, that is the equation of rotational motion. Let me box it. Let me box that one too. Why not? One thing I want to be very clear and emphasize here. This equation works big N. Only about center of mass. So this equation in principle only is valid when you calculate all your moments about the center of mass and your moment of inertia about the center of mass. Let me write it better. This bothers me. If you calculate your moments about any other point, with some exceptions, you'll see what exceptions, the equation will be wrong and you end up with wrong calculations. So always note that these equations work for center of mass. And you can imagine why center of mass. Center of mass is essentially the central sense of a body. The body is evenly distributed from our direction, so it is a center of symmetry of the body. And because of that, you can think why it is so important in rotational domain. You can kind of think if you have an unbalanced wheel, how it wobbles around. It is because you're not rotating about the, you have this asymmetry about the center of rotation, so things don't work nicely. It is the same concept related, but yeah, that is equations of rotational motion. One thing I want to mention here is that in the translational domain, we didn't have to worry about these couple moments of two forces that are, let me write it here, couple moment. So you had two forces equal, opposite, a distance d apart. If we have these kind of situations, we can equivalently take them as just as an external free moment. That one is F times D, its magnitude is that much. These couple forces don't show up in translational equations because one force, the two force vectors cancel each other out, but their rotational effect persists. So when calculating the total moment, you also have to take into account these external pure moments in your calculation. They add up in the total moment. But these moments, then the nice property of these couple moments is that they are free vectors, essentially. You can, calculating the moment of these two parallel, opposite, distant apart forces about any point will have the same effect, same moment. So really it doesn't matter where you calculate the moment of that and where you place these free moments. They have the same rotational effect. The only thing to note is the sign, whether it is in the same or opposite direction of what you have assumed. Okay, that's that. Let me do this, make it red. Okay. So this equation only works about center of mass. What about other points? You are kind of in luck, kind of you're not, that it doesn't work about most other points except a few situations. Which one is better? Let's start with the simpler one. So rotation about a fixed point. If you have a point on your body that has zero velocity, that includes a point that is fixed in a space like a hinge, or it can also work for central instantaneous center of rotation. In that case, when you have a fixed point, you can also, again, proof in the textbook, you can calculate your moment. Let me draw a figure so we know what terminology we're using. This is a fixed point. You can write, let's call it O. Sum of moment about that point O equals moment of inertia about that point, new point O. It's no longer moment of inertia about the center of gravity times angular acceleration. This works for actual fixed points like hinges or instantaneous center of rotation. If you don't have a fixed point, but somehow you're, I don't know, tempted, your heart desires to calculate or write equations of rotational motion about some arbitrary point. So let me write this as, what do I write as the header? equation of rotational motion about arbitrary point. Long header, but useful. So again, you have your random shaped body. This is center of gravity. For whatever reason, I don't like it. And I want to write this is G, my equation of motion about arbitrary point P. On the body or anywhere off the body. Really doesn't matter. But it is a point somewhere in a space. So in this case, the easiest way to think about it, if you have a whole bunch of forces and some moments on this body, note that the rotational effect of these must first of all rotate the body and also create these accelerations of center of mass too. So your forces must create two things, both turning the body as in its moment of inertia and also accelerate the center of mass, linearly accelerate the body too. So in your calculation, you have to calculate that. So if you want to take all the moments about this point P, you have to rotate the body, Ig times alpha, but also accelerate the center of mass. It becomes the equations in 2D. So let's go, why did I do that? Let's make this like this. This is X, this is Y. So your center of mass being at a distance X sub G and Y sub G. You have to account for these, essentially the moment of linear acceleration, which is going to be xg times m-a-y minus yg times m-a-x. Let me double check the signs. Yes. So you have to take into account these linear accelerations. These two are distances of center of mass from point P, noting the signs. So this could be positive or negative depending on which direction in the coordinate frame you are. If you want to think of it slightly better, remember I mentioned this equation is really a vector equation. An easier way to remember it is moments, which are all rotational, so they are all about k or z, is Ig times alpha, which is also about k, plus this R of G cross M Ag. This is an easier way to remember. And what you're dealing with here is the moment of linear acceleration. You're adding the moment of linear acceleration to your, total acceleration-y terms. Okay. Oh, wait a second. I didn't box this. Okay. This is good. So I have essentially three conditions. You can always, whenever in doubt, do this. Always write equation of motion about center of mass. And note that you calculate both the moment of inertia and your moment about center of mass. Alternatively, if you are lucky and there is a fixed point, you can calculate all your moments about that and all your moments of inertia about that point. You can use parallel axis theorem, for instance, for moment of inertia. Or if that doesn't work and you still want to calculate about some arbitrary point, you calculate moments about your desired point. You keep moment of inertia about center of gravity, and you add these distances of center of gravity to that point P. Yeah. And all of these combined with the beloved translational equation gives you full description of both translation and rotation of a body. Let me just double check if I'm missing anything. No, not really. Oh, one quick thing that, although maybe not necessary to mention, if you have pure translational motion, if you have pure translational motion, obviously you only have the translational equation of motion. So sum of your forces must equal mass times acceleration of center of gravity. But because you don't have rotation, means you don't have rotational acceleration, angular acceleration. Your sum of moment about center of gravity must add up to 0, or its equivalent form in other places. When you have rotation, well, you have it, go calculate it. Yeah, I think that is all. A busy slide, but really take-home messages are 4 boxed equation. Depending on the situation, you can use one or another to simplify the problem. All right, that is all I have for this chapter. Concepts, well, kind of simple, not too many concepts, but we'll see a whole lot of examples and different ways this naive looking equation can come into play in solving the problems. So I'll stop here. Maybe this is the end. I haven't really decided. Maybe I record a few more videos. But for now, let's stop here. And maybe see you later. Maybe not. Anyhow, take care.